Now, there were some problems with the particle model, and there's some problems with the wave model. It's not immediately obvious how we're going to calculate the energy from that. But let's build a new model which puts both of them together using the de Broglie relation. Now, to do this, I have to do a little bit of algebra. I'm going to eliminate some variables that aren't easy for me to deal with. For example, I don't know, I can't see the electron, so I don't know what the speed is. So I'd like to eliminate speed from my final expression. Let's take a look at the de Broglie equation. If I rearrange that a bit, if I solve it in terms of speed, I'll get that. So I can take this result and I can substitute it in for speed in my equation up there. Then I'll have E equals 1/2 m this thing squared. Which I guess I can simplify a little bit, right? There's an m divided by an m. Well, let's take these parentheses off first. So I just squared everything inside the parentheses there. And I have this expression, and I can see a way to simplify that because there's an m on top and an m squared on the bottom. So far I have E equals h squared over 2m lambda squared. Now the next thing I'd like to eliminate from my energy expression is the lambda. And I can do it with this. If I solve this wave model restriction for lambda, I can see that lambda is going to be 2L over n. So I can replace wherever I see lambda with 2L over n. And that's going to be alright. This is almost where I want to be. I just have to simplify this. Let's take the parentheses off there. Then I have E equals h squared on top, 2m, 2 squared is 4, L squared over n squared. Okay, there's a 2 times 4, so that's an 8. L squared. And if I multiply the top and the bottom by n squared, I can move that n squared up here. Now you might be thinking, wow, you did all that algebra pretty fast. I don't know if I can follow that. Well, you can stop the video at different points and take a look at what I did. But you know what? The algebra isn't the important thing. And I'm not going to ask you to do any calculations with this equation. But I do want you to know that this equation exists, and I want you to know how I got it. So, if I ask you, how did I get this equation, which tells me the energy levels for the electron on a wire? You'll say, you got a particle model, and you calculated the kinetic energy for the particle. You got a wave model, and you saw that there were restrictions on the wavelengths. Specifically, the restriction is there is an integer number, which we call the quantum number n, of peaks and troughs, which are half wavelengths, along the length of the wire. And then you took these two models, each of which had its own problems, and united them with the de Broglie equation, which the de Broglie relation is all about uniting wave and particle behaviors, and that's exactly how we've used it here. Now this is a master equation for the electron on a wire. What does it tell us? There's a couple of points I want to make here about this equation. Point 1. Can the energy ever be zero? Well, H is Planck's constant. That's never 0. 8 is never 0. The mass of the electron is not 0. And the length of the wire can't be 0. What about n? Well, n is the number of peaks and troughs, and there has to be at least one, or you don't have a wave. So the energy is never 0. There's always some energy that you can never take away. The lowest possible energy is the ground state energy for this, E1, and that's if I put a 1 in for the n. So then I would have h squared over 8ml squared. That's the energy of the ground state for the electron on a wire. If I was going to make an energy diagram, I could put E1 there on the bottom. And where's E2? E2 would be, I'd put a 2 in here for n. Now you can see that what you got here is 4 times E1. So if you figure out what E1 is here, 4 times that is what E2 is. And then you can very quickly get the other energy levels. E3 is going to be 9 times E1. See? So you can build up an energy level diagram for this, and we're seeing where the energy level diagram is coming from. It's a different energy level diagram than we see for the hydrogen atom. This is not the Bohr model. This is a different model. This is the model for our electron trapped on a wire. But it's giving us some of the same features. It's giving us the fact that we have quantized energy states. Now, let me go back to the fact that the energy is never 0. There's some energy, E1, that you can never take out of the system. There's always residual energy there. What does that mean? If the electron always has got energy, that means the electron is never at rest. It's always moving. Now, if that's true in an atom as well as on the wire here, that would resolve the collapsing atom paradox, because we could say the electron is never going to be captured by the nucleus. So that's a big payoff of this quantum mechanical treatment. We resolved the collapsing atom paradox right there. We also saw how we have quantized energies, and we saw where quantum numbers come from. They come from restrictions on the allowed waves. Our restrictions were, for example, that we had to have nodes on the end of the wave, or on the end of the guitar string, or else you'd be tearing the string off of the guitar. There are only certain wavelengths that are allowed, so there's only certain energies that are going to be allowed as well. And there's another payoff for this. This equation is a crude model for things that happen in plant pigments, and it explains why different molecules have different colors, and we'll talk about that in the next frame.